In terms of manufacturing, we use several processes to best build our design. Firstly, we used a box cutter to cut the balsa. We did this because balsa is very soft and using a traditional hacksaw might have caused damage. To fix the balsa together, we used hot glue to form contact patches with the balsa. This was also used to provide a secure base while used in conjunction with our 3D printed feet. The feet were printed out of silver PLA with 20% density. We calculated this density to be just enough to support our product. Finally, we used split pins to connect our X-beams together. These provided some extra support in order to prevent failure of the structure.
We needed to calculate the resource budget for our structure. To simplify things initially, I only considered the length of the wood. The total length of wood we get for free is 7.3 meters, not including the sheet. I didn't include the sheet in the budget since we planned to utilize a portion of it as support for the water container. We could decide later if we needed to cut it into additional strips. Regarding supplementary material, we could buy 1.8 meters of the wide balsa strips, 3.6 meters of the smaller balsa, or 4 meters of straws. While the straws were tempting due to the highest length offering, we were worried about how many joints our structure would require if we used many 20cm straws. Because of this, we decided against buying straws. The 9mm wide strips were the best value in terms of volume, so we decided to buy them. The final length available for our structure is 10.9 meters of balsa, or, assuming a cuboid design, 2.7 meters per side. I also wanted to calculate the volume of the PLA available to us, so it was easy to visualize how much the structure could be 3D printed. At 100% infill, which is quite rare, we can create a maximum volume of 40 cubic centimeters. At a more common 50% infill, 80 cubic centimeters is possible, or, in other words, a 4.3 centimeter wide cube. This is a slight overestimate as the walls of a 3D print must always be 100% PLA.
We had some spare material available after the construction of the final structure, and this begged the question as to how would be best to use it. This led to implementing a T-beam in the lower members to reinforce them. We then compared the second moments of area of the proposed T-beam and the rectangle respectively to find the best solution. We found that the T-beam orientated in the Y direction would give us the most resistance to bending. Using the second moment of area we calculated previously, we find that it also gives us the highest critical load, meaning a greater force is required to make the member buckle, and thus the ideal way to use our spare material.
On the top? Yeah, but is it going to all the way? Oh, is it drilling or just cutting? Yeah. I'm not drilling this bit. It's not even. Ready? Yeah. Ready?
Make sure it's in line with this beam, like the two things.
Yeah, perfect one, perfect.
Okay, so it's going to be a quick halfway. So we are at 4 already. That's fine.